We have our merry-go-round. It has a mass of 200 kilograms. There are 4 people that are at the edges. And the system is spinning at 6 radians per second. There we go. Now, in the second part of the problem, we're going to maintain that speed, but the kids are all going to walk, I don't remember exactly where it said, right to the center? Is that true? Somebody help me out and tell me what the problem actually said. 1 meter towards us. So they're just going to be halfway. Thank you. There. All right, so the moment of inertia of the merry-go-round is a disk, and that's going to be the same for both. So that's 1/2 times 200 times 2 squared, right? Moment of inertia of the merry-go-round. But we're going to have the initial moment of inertia of the kids, which is going to be 4 times, I don't remember their mass either, 60? 4 times 60 times 2 squared. There are 4 of them. They each have a mass of 60, and they're at the outside edge. And then there'll be the final moment of inertia of the kids, which will be 4 times 60 times 1 squared. Right, so the moment of inertia of the kids and their contribution to the system gets smaller. So if we add these up, we'll get the total moment of inertia both before and after. So before, let's see, that's 100 times 4, so this is 400. And 2 squared is 4, times 6 is 240. 240 times 4, is that 720? Oh, or is it 840? Somebody needs to do the math. It's too early on a Tuesday. What is 240 times 4? It is 720? 960? All right. So don't always believe me. I'm pretty fast sometimes, but not always. So that's the moment of inertia of the system before the kids walk to the center. And this will be the moment of inertia after they walk to the center. This one's easier because it's 400 times plus 240. So 9 and 4 is going to be 1360 kilograms meter squared. And after, it'll be 640 kilograms meter squared. But the angular speed is maintained. Obviously, the angular momentum changes, but we're not interested in that. They asked us how much work is done. Work is the change in kinetic energy. So the initial kinetic energy, or the kinetic energy before, is 1/2 I omega squared. And the kinetic energy after is 1/2 I omega squared. I mean, clearly the kinetic energy is less. So although the motor was doing work on the system, the motor was taking energy away from the system because the thing wanted to spin faster and couldn't. It had to stay at a fixed 6 radians per second. So there's probably more to this question. What else is there on this question? Because I don't have it in front of me. I could pull it. If I pull it. So although the kids are making it go faster now that the momentum is conserved and the kinetic energy goes up, there was no torque on this system. Work was done, but no torque because their force is towards the center and it doesn't apply a torque. It asks us to figure out the mass, the center of mass, and the moment of inertia. So let's give some parameters here. We know that the mass density is linear, so it just means that it starts at 0 and gets greater and greater in a linear fashion. There's a lot of things that would do that. A triangular shaped spoke would have a linear mass density. So it would just get greater and greater in a linear fashion. The issue is C is how fast the mass grows. We know that the entire length of the rod is L, so I'm going to treat this side as 0. And that's about all we have. So the first question, asking what is the total mass of the rod, might seem a little bit weird. So let me show you how that's done a little bit. It's not too much. And I want to start by saying you guys do remember that our definition of moment of inertia is r squared dm, and our definition of center of mass is r dm over, well, in this case it's linear, so we'll say x dm over dm. The denominator of this is just the total mass. So that's what you're being asked to find first. Add up all of the mass of the object. So that's where we'll begin, with the denominator of this fraction. So I'm going to start with the same way we started doing moment of inertia. I'm going to identify a piece of the object somewhere in the middle of the rod. We're going to try and define this piece of mass. And that's exactly what I'm going to call it. I'm going to say it's a piece of the total mass. And so I need to do two things about it. I need to find a way to point at this piece, and I need a way to define the size of this piece using the pointer variables that I choose. This system is linear. So to point at this piece, I'm going to use the measurement x, where x is the linear measurement from the light side to where my piece exists. And I'm going to say that my piece is a little more in the direction of x. So far, nothing different than when we did this as a uniform rod. But we are going to have to do something different here. Was it a good tune? So we need to come up with a way of expressing the mass density. And I will remind you of how we did this before, but we're not going to be able to do it this way this time. Last time we took the entire mass and related it to the entire length and said that this would be equal to dm over dx. We can't do that this time for a couple of reasons. One of them is because we don't know the entire mass, so it makes it so we can't do that. The second is because this isn't uniform. And although this equals lambda, this is changing for every single piece of mass. So instead what we're going to do is we're going to set it equal to the expression they gave us. And they said that the object they give us an expression for the linear density. So we will set this ratio of the mass per unit length to the equation that they gave us for mass per unit length. And then we're going to solve this for dm. So we'll get dm equals cx dx. I'll remind you that what you're trying to do is find an expression for the piece of the mass that uses pointer variables so that we can integrate from the first piece to the last piece. So what we've got here is something that represents the piece of the mass, how much that piece has for mass, and we have set it up so that we're using a pointer variable where I can point to the first piece is at 0, and the last piece is at L. And so we're going to add up every piece from 0 to L. So that means constructing an integral. Now, we've never constructed this particular integral before because we've never had to. All the other examples we've had, they gave us the total mass. So this time, we're going to have to construct an integral. It's not a huge deal. We want to just add up every piece of mass, starting with the first piece and ending with the last piece. This should give us the entire mass of our bar. Now we're going to substitute in something about the shape and size of the bar, something that we can use to address the first piece and the last piece. So we're going to substitute cx dx in place of dm. Now, assembling our integral usually is the hardest part. And I say usually because sometimes it's not. This was not particularly hard, but you've never done it before. So that makes this unique. But now that we've kind of substituted everything in, what we're going to do now has nothing to do with physics directly. It's a procedure. We're going to do the integral process. And the integral process has two parts: finding the antiderivative and then plugging in our limits. Now, it's important to understand that things that are constant means they're going to be in every single one of the terms of our summation. We can pull them out. We have at least one constant here. This value for C is going to be in every single term of our summation. So like any other summation, we can pull that out front. And now what's left, hopefully, is something that we have an antiderivative for. We're told to find the antiderivative of x with respect to x. So we're going to find the antiderivative here. We're going to use the polynomial method. This is x to the 1 power. And if I recall correctly, to find the antiderivative of a polynomial, we add 1 to the exponent and divide by the new exponent. So I'm going to add 1 to the exponent. 1 plus 1 is 2. And I'm going to divide by the new exponent. That's 2. And I'm going to evaluate this from 0 to L. So after doing the antiderivative, the next part of an integral is to plug in the limits of integration. We plug in the upper limit, then subtract, plugging in the lower limit. So this will be c times L squared over 2 minus 0 squared over 2, giving us a mass of c L squared over 2. All right. Now the next two processes are going to be almost exactly the same as that. So are you ready to go on to the next process? All right. We're going to find the center of mass of the system. So the center of mass of the system is going to be this. And we've already done the bottom part, so now we're going to do the top part. So we'll just do the top part by itself, and then we'll divide the two. Is that okay with you guys? All right. We already have an expression for dm. So I'm just going to use the exact same expression because it's already in terms of x. So off to the side here, I'm going to say that the integral of x dm, which is the top part of our fraction for the center of mass, is going to be equal to the integral of x times cx dx. And we're going to do this from the first piece to the last piece of the bar. And once we have dm, we can use it over and over and over again. So that's all we're going to do here is use it over and over and over again. This really doesn't have much for us to do, but we'll do all the pieces here. I'm going to pull out any term that is constant. That's the c, so the c will come out front. That's going to leave me with an x squared dx. This is still a polynomial, so I'm going to use the polynomial rules here. So I'm going to add 1 to the exponent and divide by the new exponent. So this will be x cubed divided by 3, evaluated from 0 to L. Any question about that? We add 1 to the 2. That gives us 3, and we divide by the new exponent 3. All right. I'm not trying to skip steps, but I think we can kind of see that that's going to be the top part of our fraction. But this isn't the center of mass. And the center of mass is a ratio, and it has this integral on the top, and it has the total mass on the bottom. So if I want x center of mass, I have to divide this by the mass of the bar, which is c L squared over 2. So I'm noticing that some of the L's cancel and the C's cancel. So if I get that out of the way and that out of the way, looks like I'm left with 2/3 L. Now, I want to point out something here. You are looking for a center of mass, a location. This is a location, and notice it doesn't have C in it either. The fact that this was linear just means that no matter what your object shape is, if it has a linear mass density, the center of mass will always be 2/3 away from where the light side is. Again, this is a triangle. If you did this as a triangle, this is what you would get for your answer for a triangle. If you guys know what I mean when I say a triangle, I'm saying, what if your bar looked like this? You may not know how to do this, but you can break this up into little slices that are getting bigger and bigger all the time. This would have a linear mass density. And it would tell you that right now what we've just found out is that if you go 2/3 of the way from this end, that's where the center of mass of any triangular bar would be. What's funny is it doesn't even have to look like that. That looks like a bar, clearly, but even if you had a triangle like this, if you're trying to spin it from here, 2/3 of the way from here would be the center of mass. Because this also has a linear mass density. It's any triangular shaped object would be like this. So, all right. Our last step is to find the moment of inertia of the bar. So that's going to be here. It's been a while since we've done this, and I want to remind you what R stands for. R stands for the perpendicular distance from the axis of rotation to where each piece of mass is. So is it too big a stretch for you guys to accept that R is X for this problem? Because X is clearly the perpendicular distance from the axis of rotation to our piece of mass. So our moment of inertia will be the integral from 0 to L of x squared dm. Again, I already have an expression for dm. I'm going to use it again. So this is going to equal the integral from 0 to L of x squared, and in place of dm, I'm going to put cx dx. Again, I have a constant, and I'm going to collect it and bring it out front. Looks like I'm going to be left with x cubed dx from 0 to L. Have I done this enough times now that you guys can do this one? You should. Because I've performed this twice, and it's been exactly the same each time. Why don't you perform this one and show that it equals what's in our problem? We affix the bar, and we're going to let it swing. So we're doing it about the light end. I'm going to go ahead and use something that more visually represents what's happening. So this, and we are fixing it to the end here. We know the center of mass is right about here at 2/3 L. And we want to know how fast is this swinging when it makes it downwards. So it's going to swing and become, let me just duplicate that. So make it down like that. So we want to know I think it said the angular speed. Is that correct? All right. So this is a conservation of energy question. And the bar has gravitational potential energy here because our center of mass is above the lowest position it's going to swing to. So I'm going to set the reference level to be at this position, because this represents the lowest place that the center of mass will make it to. And I'm going to base the amount of potential energy we have on that change in height. So I'm going to say that the potential energy is 1/2, I'm sorry, what am I doing? mgh. mg, where h is going to be 2/3 L. it's going to swing downwards, and all that potential energy is going to become rotational kinetic energy, not translational kinetic energy, rotational kinetic energy. It has a fixed pivot point, so this object won't have translational kinetic energy. So down here, 1/2 I omega squared, and we're looking for omega. This part's not trivial. The mass just doesn't cancel out like we would have expected in other examples like this. We'll have to substitute in our expression for the mass and our expression for the moment of inertia. So the expression for the moment of inertia was CL to the 4th over 4, right? I don't remember. Well, you can just make it up if you guys don't remember either, but there, omega squared. So we'll have that, and our expression for the gravitational potential energy will be CL squared over 2 G times 2/3 L. Any question about those substitutions? Again, they gave you all of this, so you might have been able to work this part out. I'm just going to set these two things equal to each other because there's a bunch of stuff that's going to cancel out. So let's go ahead and get that together. 1/2 CL to the 4th over 4 omega squared equals, looks like I have 2. 2's cancel there. So CGL cubed over 3. Did I collect all those okay? Hope so. 2 times 4 is 8, so we can do that. And I think we're going to get the C's to cancel and a bunch of the L's to cancel. So I'll have L omega squared over 8 equals G over 3. All right, just doing some algebra. So I want omega. So omega squared equals 8G over 3L, and I'll take the root and get 8G over 3L under the radical. Man, hard to know if we're right or wrong here, but we can test our units. That'll help. G is in meters per second squared, and L is in meters, and that's all under the radical. The M's cancel, which leaves us with nothing up on top over seconds squared. If you're doing work on a problem that's rotational and you get no units, what are the units? Radians, that's right. So this will be radians. So we take the root and we'll have radians per second. So we come out with the right units. That's probably pretty good. All right. So we have to do the problem again. I don't really want to do the problem again. You just have to find where the new moment of inertia is. But also the change in height is not going to be 2/3 L. The change in height is going to be 1/3 L because we're swinging at about the heavy end. So I'll at least do this, show you how to set this problem up, but I think it would be best if you guys do this. Now that you've kind of seen it all done. We're going to be affixing it to this side this time. And our center of mass is here. So when this thing swings downwards, it's going to swing so that kind of looks like that, where our lowest point for the center of mass is now going to be 1/3 L. But you need the new moment of inertia. We have the moment of inertia about the end, and that moment of inertia was CL to the 4th over 4. And you need the moment of inertia about the heavy end. So you can use the parallel axis theorem here, but you have to move the axis to the center of mass first, and then move it from there to the end. You can do it in a couple steps. You can do the algebra, but it's going to be CL to the 4th over 4 equals I center of mass plus mx squared, where you have to figure out what x was to shift it from the center of mass over to here. It's not too tough, but that's how you would find the center of mass, moment of inertia. So this will be CL to the fourth over 4 minus mx, but in this case, x, the shift distance, was 2/3 of L. So minus m times 2/3 of L squared. And that's going to equal I center of mass. But you also have to sub in our expression for the center, for the mass of the bar, which is CL squared over 2. So this isn't necessarily easy to do. In fact, I think it would have been easier just to find the new moment of inertia using integral calculus. Because just so you know, if you had done this using integral calculus, you can just do the same integral again, but change your limits a little bit. But this will work. This will get you your center of mass. But then you'll have to do it again to shift it from here over to here. So that's, at this point, becoming busy work. So I'll let you guys try it at home. If you have your notes for the ring, for the disc, we can use that. We could also do it a different way. There's a couple different ways to do the disc in the ring. We did it using a square of mass. Like we said, okay, there is a square of mass here. And we talked about the size of this area. And we said that that area, the ratio of the mass to the area, would be the ratio of the entire mass of the disc to the entire area of the disc. When we did the disc, this is how we set this up. But then we changed dA, and we said that dA would be equal to, and we zoomed in, if you'll recall, and we took the center to be here. We said as a reference point, we'll make reference from the top, and we'll say we will go over a distance theta, and we'll go out a distance r. And then we would said that this side length from here to here was a little more in the r direction. And we said that this side length from here to here was an arc length of r d theta. And so if we multiply these two sides together, that would give us the area of the box. So I don't know if you guys remember all that, but it's all in your notes. We've done this one. It's just been a long time since we've done this one. So what I had said to you then was, well, we're going to say that our area is dr times r d theta. That will be dA. And we'll sub it in here for dm over dA, which is r dr d theta. I'm putting them in a different order, but I'm just grouping the r and the dr together and putting the d theta separate, equals mass over area. Any question yet? Okay. Now, we have to solve this for dm, and that's going to be mass over area times r dr d theta. I'm going to leave it as just mass over area. Those are constants. Does that make sense? You guys remember that, right? Those are going to be constants. So they're just going to be constant in this, and we'll plug that in a little bit. I mean, mass is just going to be m. We are going to have to do something for the area because the area is not pi r squared. So we'll have to do something for the area towards the end of the problem. We'll come back to the area in just a few minutes, if that's all right with you guys. Let's do the heavy lifting. Let's do the calculus part. The calculus part is us to remember that this is going to be the integral of r squared dm, where r represents the perpendicular distance from the axis of rotation to our box. Is it clear to you that the r that I have here is the same as the r that's there because those both represent the perpendicular distance from the axis of rotation to the box? Good, good, good. So integral of m over a, r dr d theta. We can collect and move our constant out front, get our r cubed inside here, but there's two derivatives, so I have two integrals, one for dr and one for d theta. D theta is going to be easy. We're going to go around the whole circle again. So d theta is going to be 0 to 2 pi. But r isn't going to go from 0 to r like we did last time. We're going to go from the inner radius, ri, to the outer radius, ro. Because we're not going to do the inside because there's a big hole in this one, right? So we don't include the hole. And so let's go ahead and split our integrals to make it easier and have the integral from ri to ro of r cubed dr and the integral from 0 to 2 pi of d theta. Any question where I came up with any of that stuff? Because so far the only difference between this and the first time we did it is that right there. That is the only difference, is that we're not integrating from the inside all the way to the outside. We're integrating from the edge of the thick ring to the outside of the thick ring. That okay? All right, well, the rest of this math is pretty straightforward because we've kind of done this one before. So m over a here, the antiderivative of r cubed is r to the 4th over 4. Evaluated from r inside to r outside. And the integral of d theta is just theta, evaluated from 0 to 2 pi. So m over a times r outside to the 4th minus r inside to the 4th times 2 pi. Okay, all that's looking pretty good. Looks like I can factor out a pi and cancel out a 2. Do you guys see that? But we have to deal with A. We need the area of the thick ring. Now, that's not too tough. It's the area of the whole thing minus the area that's of the hole. That would be the area of our object. Everybody follow that okay? So we'll have to sub this in for area here. And that's making this look way complicated. But I know math things, and I know we're going to get some simplification in just a minute. You hopefully will know math things. All right, so I pulled out some stuff, like the 4, I pulled it out. The 2 pi, I pulled it out to the front. We're going to cancel out all the pi's. We're going to cancel out the 2 with the 4. So we have some stuff that's going to reduce. But I know what the difference of squares is. Do you guys know what the difference of squares is? If you do, then you know we have a reduction we can make here. If you don't know what the difference of squares is, then you're at a loss. You should know the difference of squares. So I'm looking at this right here, and I'm talking about the difference of squares for that. So if I rewrite this, 2 pi m, oh, actually, let's just go ahead and get rid of the stuff that we don't need to, so we'll get rid of the 2 pi. So that's just m over 2 times ro squared minus ri squared times. The difference of squares lets me take this and rewrite it as the product of 2 squares. That's the difference of squares. You guys, because the cube, going to the 4th power is still a square. So I can change this to the difference of squares. If you don't know this, FOIL that. You'll find that it becomes what we just had. But you should know this one. This is one that's worth memorizing because it was all over Algebra 2. It's all over pre-calc, and it'll probably be all over calculus because you use this a lot for simplification. And by doing this, we cancel out one of these. Which is why the answer, which is on the equation sheet at the front, is 1/2 m, the sum of the radii, which seems kind of weird. But that's how it is. So that's the moment of inertia of a thick ring. The rod sphere bug system swings about the axis. At the instant the rod is vertical, as shown above, determine each of the following. The angular speed of the bug. I probably can't unless I know more things. So the bug is 3m, right? So this total mass here is 4m. And this mass here is m. Is the whole thing L or is the whole thing 2L? Okay, so this distance is L. All right. So the moment of inertia of this system is ml squared plus 4ml squared, 2-point masses. I can ignore the rod, I think. So that gives me a total moment of inertia of 5ml squared. You can do this either as a net torque about the center of mass, or you can do it as two separate torques. I'm going to do it as two separate torques. There are a torque here that is equal to L times 4mg. There's a torque here that is equal to L times mg. These two torques are, actually no, I can't use torque because the torque is changing the whole time, so I guess I'll have to use energy. So we'll use energy instead. This would give us the acceleration. If that's a question, we'll need it, but no, we'll need energy. So right now, this bug, which was here, has gravitational potential energy relative to its lowest position. So it has, before it begins to swing, a gravitational potential energy of 4mgl. This is the only energy in the system before. After, we've got, let's see, this bug is at its lowest, but this bug started here and went upwards, so it has gravitational potential energy of mgl, plus the two-bug system has kinetic energy of 1/2 I omega squared. So if they want the angular speed, this seems like the right way to go. So that's what we'll do. That will mean that I have 4mgl equals mgl plus 1/2 I 5ml squared times omega squared. All right, before and after. I don't know why there's a second equal sign there. That should be a plus sign. Subtract and get 3mgl equals 5/2 ml squared omega squared. And solve that for omega. Want me to keep going? You sure? The angular momentum of the system? Well, I'll need omega for that, so I guess we will keep going. Cancel out the m's, divide by L squared, and my 2/5, so 6/5 G over L. Take the root, that's omega. So the angular momentum of the system, L, is I times omega, or 5ml squared times the square root of 6g over 5L. So yes, I can find the angular momentum. You could probably clean that up a little bit, but it's not going to look great no matter what you do. Like you could put some of that stuff inside the radical, but I'm not sure it's worth it. The magnitude and direction of the force that must be exerted on the bug by the sphere to keep the bug from thrown from the sphere. Do I need to do all that? That's just net force equals MAC on the bug. The bug has a mass of 3m. Don't forget, don't put 4m because it asked about the bug. And you have omega squared times L. So this has to be the force, the net force on the bug. Be careful, that's the net force on the bug. The bug's experiencing two forces. Him holding on with his little buggy feet, so force on the bug, and mg. So make sure you understand that. Net force will be F from the bug minus mg equals 3m omega squared L. And this will give you the force that the bug needs to have to hold on to that little thing as the thing swings down through the lowest point. A lot of students forget this for some reason. I don't really know why. Yeah. The net force has to be upwards, or the bug can't travel in a circle. I mean, I think the picture says it's upwards, but it's okay. I don't mind repeating myself or reiterating it. That's the right word. I'm not repeating. With a bar, and I'm going to draw it not as a bar because the truth is it's got a density that is linear, a linear mass density, meaning that it increases in a constant way. That's a triangle. A triangle would do that. So that's what this bar really looks like. If you spend any time with this, you can, and if you know a little bit of math, you can prove that this has a linear mass density. You do so by just taking a slice of it, say here, and work out based on where you are and how wide this piece is, what the mass of it would be using just areal density. So it can be done using some basic math stuff. I'm not going to go into it because I don't think you guys would appreciate it, to be honest. But I'm going to choose a piece of the bar. And I'm going to do the exact same process that's already in your notes that you guys probably wrote down, but didn't commit to it by trying it again or practicing it. So this begins with us remembering that we are identifying a piece of mass of the bar. And we're going to call that piece dm. In the future of this problem, there is a future where we're going to take the mass divided by the length and set it equal to a piece of the mass divided by what we're going to call a piece of the length. This is going to be the linear density. This is a part of all the problems in which we're trying to figure out center of mass or moment of inertia. But before I do that, I do need to come up with some parameters for how I'm going to point to this particular piece of mass and how I'm going to deal with its size. So I am told that I need to get everything with respect to the light end. So I'm going to set a pointer here and set this equal to 0. And I'm kind of indicate that the bar has a length of L. So I'm going to say the entire length of the bar from 0 goes to L. I'm going to use the counter or the variable x to define where the first box is and where the last box is and where every box in the middle is. And I'm going to say that this box is dx wide. Any questions about those choices? All right. Then my density is going to be that m over L is to dm over dx, except that this isn't uniform. So I have to use an expression for the linear density that was given to me in the problem, because this box has a different mass than, say, this box over here, even though they're considered to be the same size. They're the same dx. But we are told in the problem that we have a mass density that gets greater as we go from 0 to L. Now, question A asks us to find out what the mass of the box is. We haven't done one like that, but we haven't been given a problem where we didn't know what the mass was, so this is a unique one. But it's not particularly hard. You do have to think about it for maybe, I don't know, half a second, that the total mass of the box would be what would happen if you added together all of the pieces of mass, starting with the first piece and ending with the last piece. So I need to come up with a way of writing dm in terms of x, because x points to the first piece and x points to the last piece. So I'm going to set dm over dx not to m over L, but to cx, the definition of our linear mass density. And I'm going to solve this for dm. So, job 1, let's find the mass. I'm going to integrate from 0 to L, cx dx. Now, the process of integration is one that you should be learning. We have talked about it. It's 2 steps. And for us, we're always using some fairly straightforward integrands. I am going to notice that I have a C in every term in my summation, meaning that the C value is constant for every single one of my terms. So constants can be pulled out of the integration. So I take the C and pull it out front, and that leaves me with the integral from 0 to L of x dx. Now, for those of you who are maybe wanting to pay a little more attention now, they're getting close to another test and want to make sure I don't put this on there, or if they do, then you have a way of doing it. Take the antiderivative of x with respect to x. That's what that says. And so x is x to the 1 power. That is a polynomial. I will use the polynomial rule. The integral is a 2-step process. Find the antiderivative first, and then plug in your limit second. The antiderivative of a polynomial is to add 1 to the exponent and divide by the new exponent. So the c stays here, open parentheses. Antiderivative of x to the 1 is x squared over 2. I'm going to evaluate this from 0 to L, which means I'm going to put in limits in a minute. So the next part of this is just to plug in the top limit and then subtract when I plug in the bottom limit. So c times L squared over 2 minus 0 squared over 2 gives me the whole mass as c L squared over 2. Next, I need to find the center of mass. The center of mass is a ratio. And so if you look on the equation sheet, you find that center of mass is going to be the ratio of x dm divided by the total mass. Luckily, we just found the total mass, but now we have to do the other portion, which is the weighted average. We're going to add up each piece of mass and where it is relative to my starting point. And my starting point is going to be the end. Now, there really isn't a lot to do here. We already have dm. We're going to continue to use dm for the remainder of the problem. So x center of mass is going to be the integral of x, which is just what we have here, times cx dx. I'm plugging that in for dm. Just taking that and subbing it directly in. Have fun. We're still going to evaluate this from 0 to L, and we're going to divide this by the total mass. Now, obviously, I'm mostly interested in what's happening on the top right now. So maybe we'll just focus on what's happening on the top right now, and then we'll divide by the mass at the end. That all good for you guys? So again, I'm going to do a few little things. I'm going to take the value that is constant, that has nothing to do with x, and take it outside the integral. So c comes outside the integral. I'll take the two x's, multiply them together, and get x squared, and evaluate it from 0 to L. And at the end, I'll divide by the mass. Now, we kind of just did this. I'm just going to do it again. This is the antiderivative of a polynomial. My polynomial is x squared. So I'm going to add 1 to the exponent and divide by the new exponent. So leave my c there. This will be x cubed divided by 3, evaluated from 0 to L, all divided by the mass. Questions? Alrighty. So the top's going to be CL cubed over 3, and the bottom is going to be CL squared over 2. This will be the center of mass. I just plugged everything in because you guys are clearly bored. This must be beneath you, so not much to do here. Cancel out the C's, cancel out the L squared, and we'll get 2/3 L. We're going to have to get something that probably has a location in it. This has a location in it. If you think it's weird that C isn't there, that is a little bit weird, but it's because it's linear. That's really what it's about. The fact that it's linear here determines where this is going to be. this hadn't been linear, like if the mass had increased at the rate squared or something, it'd be someplace else. But it being a linear function produces the same response no matter how long the rod is. It's always going to have a mass 2/3 away from the light point. What's interesting is it doesn't matter what your triangle looks like. If your triangle looked like this, well, this is the light point. The center of mass would be right there, 2/3 away. So it's 2/3 along the height of or the altitude of your triangle. It's true for every triangle, every isosceles triangle. But okay. We have one more thing to do. Moment of inertia. So I guess we'll do that right here next to us. So if you don't remember, moment of inertia is the integral of r squared dm, where r represents the perpendicular distance from the axis of rotation to our location of the mass. I think we're using x as that pointer variable. Because of that, I'm going to substitute x squared in for r squared. So I will write this again as the integral of x squared, and I will sub in for dm cx dx. And I'm going to evaluate this from the first piece to the last piece. All right, you should do this, right? I've done it twice already. The least you guys can do is try it once. The moment our object hits the part where there's a coefficient of kinetic friction, there will be a frictional force that acts on the object to slow it down. That coefficient will act here, this way. So there's other forces acting. There's gravity, and there's the normal force. So I know the frictional force will equal mu k times the normal force, which is going to be mu k mg. So this object experiences a single force that is in the x direction. So I know that the acceleration is going to be negative mu k g. Any question about that? All right. Its initial speed is v naught. Final speed unknown. Time unknown. Displacement unknown. There is a motion equation coming up. We'll deal with that part in a minute. At the same time that that's happening, there is an angular problem occurring. The object is experiencing a net torque equal to I alpha. That torque comes from the frictional force. So this is a positive torque. So RF equals I alpha. So alpha equals RF divided by I. Friction is not an unknown though, so I can sub in mu k mg. So this will be R mu k mg over I. If you were doing this in terms of one of the moments of inertia, some of this stuff would cancel out. Well, we're just going to leave it in terms of I, because that's what was requested. This object has an initial velocity of 0, a final velocity that is unknown, and a delta theta that is also unknown, and a time that is unknown. However, we are trying to figure out how far the thing slides until it begins to roll, and that's conditional. It is rolling when this is true. So we want to find out when that's true. And I say that specifically. I want to find out when it's true, because it's the only way I'll be able to find out where it's true, because I don't know anything about the relationship between delta theta and delta x while it's sliding. But the moment this is a true statement, I can figure out when that occurs and use that to figure out where it occurs. When we did this problem, we got all the way to the part where we found out when it occurs. I told you guys you should put it back in the equation to find out where it occurs. So I don't think you did. So we will do it together. I'm going to use v equals AT plus V naught. I want an expression that has to do with V. And I'm also going to have omega equals alpha t plus omega naught, because I'm going to relate them here. So I will have V equals negative mu kg times t plus V naught. I'm going to sub that in right there. And omega is going to be r mu k mg over I plus, oops, forgot the t, plus 0. And plug that in right there. All right, so negative mu k gt plus v naught equals r mu k mg over I times t times r. Right? We want to collect this for t. So I'm going to get the t's on the same side, and I guess that just means moving this over to the other side. So v naught equals mr squared mu k g over I times t plus mu k g t. So again, we're trying to find out when this happens. For those of you playing at home, you look carefully. If we had I, the mr squareds would cancel out, and we would have something that has just mu k and g in it, and there'd be some number there. Because if the I was like a disk, we'd have 1/2 mr squared here. You guys follow that? So this would be simplified, and it will simplify when you substitute an I in later. But we're leaving it in terms of I as requested. So I'm going to factor out the mu k g out front. I'll have mr squared over I plus 1 times t. I'm doing that because everything inside that parenthesis is a unitless quantity, and it is dependent on I. This is going to be some coefficient. And so to solve it for t, I'll have t equals, there's nothing special here, so it's just going to be ugly. So I'm just going to leave it nice and ugly. There's t. Good? So now you need to find out where this happens. We found out when it happens. Now we find out where it happens. You have options on this one. Not particularly good ones. So I would probably use something like delta x equals 1/2 at squared plus v naught times t. Although that looks like it's going to be super ugly. I'm not sure that's going to be great. It wouldn't be as bad when you sub the I in, but this is one way to do it. And let's see, is there another way we could do it that may be not so ugly? No, I think this is it. I think you're stuck there. Yeah. It was 0. It wasn't spinning before it hit this patch where it was, right? So we said it was starting at t equals 0 with no rotational speed. Is that okay? All right. I'm not going to do the algebra. I will do the algebra if we sub in an I, but I'm not going to do the algebra as is. So I do think if you sub in an I real quick, you'll be able to figure a few things out. For example, if we sub in an I of, say, a ring, which is mr squared, then t for the ring is going to be v naught over 2 mu k g. And if we sub in I for a disk, which is 1/2 mr squared, then this is going to be, let's see, that'll be a 1/2 in the denominator, so this would be V naught over 3. So this tells me something very clearly, that it will take longer for the ring to be rolling than it will the disk. And I expect it to take longer because a ring is harder to turn than the disk. So I would expect it will take a longer period of time for it to go from sliding to rolling. Now we can take either one of these and sub it in over here. It's going to not be so terrible now. And this will give us where it's going to happen. So let's, delta x is going to be 1/2 times negative mu kg times t squared, which is V naught squared over, I don't care, are we doing the ring or the disk? Okay, so 4 mu k squared g squared plus V naught times V naught over 2 mu kg. We're just going to do some algebra here. Delta x equals, this cancels with one of those, and I have a 1/2 and a 4, so this will be negative V naught squared over 8 mu kg plus V naught squared over 2 mu kg. So now when I can add these together if I get common denominators. So this gives me 3 V naught squared over 8 mu kg delta x. That looks crazy. Who knows? Is it right? I don't know. I mean, there's stuff in here that looks right. I have meters per second squared in the denominator, and I have meters squared per second squared in the numerator, so my units come out to be meters. That seems promising. I know that 3/8 is a product of the number that I had with my time. I'd have a different number there if I had used the 1/3 as opposed to the 1/2. So I expect to see that different. It does say that it will go further if it starts faster. Does that make sense? Makes perfect sense to me. It also tells me that it will be rotating sooner if mu k is greater. So if there's more friction, it starts rotating sooner. Does that make sense? I think it makes sense to me. It also indicates that if gravity is greater, it will start rotating sooner, but that's just a product of it increasing the frictional force. So although it may not look like it's right or wrong or whatever, it makes a lot of plausible sense. And like I said, you already have issues with the times there, so it's clear that you start putting stuff in here, you can kind of figure out which things will go further. Now, the object, is it at rest at this moment? Do you have any idea what we were solving for from the beginning? Because if you don't, then you just fell asleep halfway through because you don't have the attention span to follow it. It was 12 minutes. But it's not stopped. It's rolling now. This is how long it took until it went from sliding to rolling. In fact, we know how fast it's going. We solved for that earlier. We have an expression for how fast it's going. You plug t in for this, it'll tell you how fast it will be traveling when it's made this transition. It has lost energy, though. I do want you to know that. Energy was lost in this system. That's worth noting, because you could be asked to find it. How much energy was lost when you go from sliding to rolling? But as long as kinetic friction is acting on an object when it's sliding, it is doing negative work on your object. So energy was lost, and some of that energy was being diverted from linear motion to rotational motion. But if you add up the rotational kinetic energy and translational kinetic energy at the end of this portion of the problem and compare it to how much translational kinetic energy you had at the beginning, you'll find that this object had lost energy. There had to be some energy lost. We were dealing with kinetic friction acting on our system. So while it was sliding, it was losing energy. All right. This a hard one? Yep.